Hello, welcome to today's class. We shall be talking about energy loss in pipes. Before we talk about energy loss, what is a pipe? A pipe is defined as a closed conduit of circular section through which the fluid flows, filling the complete cross section. The fluid in the pipe has no free surface. It will be at a pressure which may vary along the pipe. Therefore, losses of energy in a pipeline cannot be ignored. When a fluid is flowing via a pipe, the fluid experiences some resistance, due to which some of the energy of the fluid is lost. We have two major types of energy losses. One is called the major energy loss, and the other is called the minor energy loss. Major losses in the pipe get accumulated over the length. However, major losses in pipeline can be brought down to a minimum by adhering to best design practices. If the pipe is long enough, the minor losses can usually be neglected as they are much smaller than the major losses. So, losses of energy are due to the following. Number one is shock loss at sudden enlargement. Number two is shock loss at sudden contraction. We have the bend in pipe, we have pipe fitting, and we have obstruction in pipe. All these are examples of minor losses. So these are examples of minor losses. Minor losses. Now, for the major losses are due to friction. So the major losses are due to friction. So friction is the main cause of major losses in pipe. So friction is for the major losses. So in this video, we shall be looking at shock loss at sudden enlargement and shock loss at sudden contraction, and finally we shall look at friction losses. So what you see on your screen is a shock loss at sudden enlargement. Now, as you can see on this video, this diagram is showing you a loss of air when a pipe undergoes a sudden increase in diameter. As you can see at this entrance, the diameter is smaller than at this entrance. So when a pipe undergoes a sudden increase in diameter, it is referred to as head loss due to sudden enlargement. And the formula to calculate the head loss can be given as HL is equal to, open brackets, V1 minus V2 or squared over 2G. So the V1 and V2 are the velocity at point 1 and at point 2 respectively. Your G is your acceleration due to gravity. So we can put that in words. So our V1 is the velocity in the smaller diameter, as you can see on the screen. V2 is the velocity at or in the larger pipe. All right, so with this we can solve questions that relates to sudden loss at sudden enlargement. Now we can also put this equation into the Bernoulli equation to find the difference in pressure. So that becomes P1 over density times G plus V1 squared over 2G equal to P2 over rho G plus V2 squared over 2G plus HL. So this is a formula we can use to find the pressure difference at point 1 and at point 2, and we can do this using the Bernoulli equation, which we have covered in our previous classes. Now I want us to also note that we have some very special cases. For example, when a pipe discharges into a very large reservoir through a sharp exit, conditions for enlargement can be different. In that case, our velocity in the larger pipe can be referred to as 0, and therefore our head loss becomes HL equal to V squared, or V squared over 2G. This is when the pipe discharges into a large reservoir via a sharp exit. Now, if the exit is round, this loss is greatly reduced and is usually negligible. So let's look at a question of how we can apply this whole concept. So here's a question. It says a pipe carrying 0.03 meters cubed per second of water increases suddenly from 0.05 meters to 0.1 meters in diameter. Calculate the head loss due to the sudden enlargement. So we can just do a sketch of the pipe. As you can see, if a sketch, it enlarges. So here is my diameter of the smaller pipe stream. I call this 0.05 meters. Then this is the diameter of the larger pipe stream. Call this is 0.1 meters. So we can call this our D1. We can call this our D2. All right. So here's our V1. Here is our V2. All right. So before we can find the head loss due to sudden enlargement, we have to find the area of the smaller diameter and the area of the larger diameter. Now we know that in fluid mechanics, the rate of flow at the exit is always equal to the flow at the entrance. So we can say that Q1 is equal to the area at point 1 times the velocity at point 1. Our goal here is to find our velocity at point 1. So to find that, we have to find our area. So our area 1 is equal to pi d1 squared over 4. That gives us pi times our d1 is 0.05 all squared 0.05 all squared over 4. Now when you put that in your calculator, our A1 should give us 0.00196 meters squared. 0.00196 meters squared. That's for our A1. Also, we have to find our A2. To find the A2 is A2, which is the area of the smaller section or the larger section of the pipe, is A2 equal to pi V2 squared over 4. So that gives us pi times my V2 is 0.1, 0.1 all squared divided by 4. When you put that in your calculator, your area at the larger pipe stream should be 0.00785, 0.00785 meters squared. So now we can find the velocity at section 1 and at section 2. So coming back to our flow rate equation, we can transpose to find our V1. So therefore my V1 is equal to Q1 over A1. So that gives us V1 is equal to, my Q1 from the question is 0.03, so I have 0.03 divided by my A1 area at section 1, which is 0.00196, 0.00196. So therefore my V1, put that in your calculator, my V1 is 15.3. I have 15.3 meters per second. All right. So let's find the velocity at section 2. And please note that the flow rate at section 1 is always equal to the flow rate at section 2. So the same thing. So my Q2 is the same as 0.03 is equal to A2 V2. So we can transpose. We have V2 is equal to Q2 over area 2. Putting our values, my Q2, remember my Q2 is the same as my Q1 because the flow rate at section 1 must be equal to the flow rate at section 2 according to the principle of continuity. So my Q2 is 0.03 over my A2, which is 0.00785, 0.00785. So therefore, the velocity at section 2 is 3.8 meters per second. It's approximately 3.8 meters per second. So now we can find our head loss at sudden contraction, which is HL equal to V1 minus V2 all squared over 2G. So we can put in our values, open our brackets. My V1 is 15.3 minus my V2 is 3.8 all squared over 2 times G. Now remember guys, my G is what? 9.81 is 9.81. So this is 15. So 15.3 minus 3.8, that gives us 11.5. So we have 11.5 squared. Two times 9.81 gives us 19.62. So therefore 11.5 squared will give us 132.25 divided by 19.62. So therefore my head loss at sudden contraction is giving us 6.7 meters. 6.7 meters. So that is the head loss due to the sudden enlargement in this system. So let's look at shock loss at sudden contraction. So here is a simple diagram showing us the loss of energy at sudden contraction. Now, sudden contraction is when the pipe suddenly contracts, as you can see at point 3 and point 2. So in sudden contraction, the flow converges to form a vena contractor at section 3, as you can see on this diagram. Now, the loss of energy in the convergence from section 1 to section 3 is very small, and the main loss occurs in the enlargement from section 3 to section 2. It is unusual to ignore the loss from section 1 to 3 and treat the loss from 3 to 2 as if it was due to a sudden enlargement from the area of the vena contractor to the area A2 of the smaller pipe. So we have to consider the loss of energy from point 1 to point 2. I know you might think that from point 3 to 2 is enlargement, but for this we have to consider the loss from point 1 to the smaller pipe at point 2. Now, in doing this, we consider the principle of continuity, and the formula we use to find the head loss due to sudden contraction is given as HC is equal to, open brackets, 1 over C subscript C minus 1, bracket close, or squared, times V2 squared over 2G. Now, the V2 is the velocity at what? The smaller pipe. Your C subscript C is known as the coefficient of contraction. 6C is the coefficient of contraction, and V2 is the velocity at the smaller pipe diameter. Now, we also have a special case right here. If the entrance of the pipeline from a reservoir is sharp, that means it is not round, it is equivalent to a sudden contraction from a pipe of infinite size to that of the pipeline. So in that case, we have that our CC becomes what? Becomes 0. So therefore, our formula becomes HC equal to V squared over 2G. That is when the pipe entrance from a reservoir is sharp. Okay, so we can use this formula to solve questions as it relates to shock loss at sudden contraction. So here is a question we can use to solve for sudden contraction. Now, how do you know it's a sudden contraction question? When the pipe diameter reduces, that is head loss due to sudden contraction. But when the pipe diameter enlarges or increases, that would be a head loss due to sudden enlargement. So let's solve this question. It says, consider a situation of water flowing vertically downwards via a 90 millimeters diameter pipe suddenly contracts to 30 millimeters with a velocity of 3.0 meters per second. find air loss if the coefficient of contraction is 0.62. So I can just draw a sketch. All right, this is a sketch. So this is the entrance. This is my V1 right here, and this is my exit. So this is my V2, and we are told that at V2 it is 3.0 meters per second, and also our diameter D2 is giving us 30 millimeters, and my D1 is 90 millimeters. Now for this question, I will not be needing my diameters, because to find the head loss due to contraction is just HC is equal to, open brackets, 1 over coefficient of contraction minus 1 or squared times V2 squared over 2G. So as you can see from this formula, I won't need to find my area because I don't need it. So remember that my CC is 0.62 and my G is 9.81. So we have to log in the data. So my head loss due to contraction, open brackets, is 1 over CC is 0.62 minus 1 or squared times my V2 is 3.0 squared over 2 times G. My G is 9.81. So therefore we have 1 divided by 0.62 gives us 1.613. 1.613 minus 1 or squared. 3.0 squared is 9 over 2 times 9.81 is 19.62. So that gives us 1.613 minus 1 is 0.613 or squared. So we have 0.613 squared times 9 divided by 19.62. So we have times 9 divided by 19.62. So therefore we have 0.613 squared times 9 divided by 19.62. Our answer should be approximately 0.17 meters. So this will be the head loss due to sudden contraction for this question. So let's look at friction loss. Now, when there is a loss of head due to friction in a pipeline, in terms of the velocity head, we assume that the frictional resistance per unit area of the pipe wall is proportional to the square of the mean velocity of flow. Now, the force acting on the cylinder is the force due to pressure difference and the force due to frictional resistance. All right, we derive, or according to Darcy's formula, the loss of head due to friction in the pipeline is given by HF is equal to 4F LV squared over 2GD. This formula is known as Darcy's formula. This is called the Darcy's formula. Darcy's formula. Now, the Darcy's formula or equation is an empirical equation which relates the head loss or pressure loss due to friction along a given length of pipe to the average velocity of the fluid flow for an incompressible fluid. So each of these parameters represents something. So I'll give us the names for each of those parameters you see in the equation. So the F is the Darcy's coefficient. Most times in questions, you are always given the Darcy's coefficient. The L is the length of the pipe. The V is the mean velocity of liquid in pipe, while the D is the diameter of the pipe. So with this, we can solve for the head loss due to friction. Remember again that friction loss is a major energy loss in pipeline. So let's look at an example of a question as regards to friction loss. Now, we're asked to determine the loss of head due to friction in a pipe 18 meters long and 5 meters in diameter carrying 1.9 meters per second oil if our Darcy's coefficient is 0.07. So step 1, I can write out my given data. I'm giving my length of the pipe is 18 meters. My diameter is 5 meters. My speed or the velocity is what? 1.9 meters per second. And my Darcy's coefficient is 0.07. And also please remember that my G is constant, which is 9.81 meters per second squared. So to find the head loss due to friction, we are given that H subscript F is equal to 4F LG squared over 2G times the diameter. So we can log in the values. So we have 4 times my F, which is the Darcy's coefficient, is 0.07 times the length of the pipe, which is 18, times my mean velocity, which is 1.9 squared, over my 2 times my G, which is 9.81, times the diameter, which is 5. So therefore my head loss due to friction is 4 times 0.07 times 18 times 1.9 square will give us 18.1944. 18.1944 divide by 2 times 9.81 times 5 gives us 98.1. So therefore my head loss due to friction would be 18.1944 divided by 98.1 will give us 0.19 meters of oil. So this is the head loss due to friction for this situation. So please, in summary, we are saying that when fluid flows through a pipe, it experiences losses, and these losses can be major or minor. And we said that the minor losses can be due to sudden enlargement or sudden contraction. It can also be due to pipe fittings, and also can be due to a bend in pipe. Now, for the major loss in pipe is due to friction. So here is a practice question for us to work out. So please do your best to attempt this question and send your worked solutions to my email address. Thanks for watching and have a great day.